Yes, sir,
yes.
we can
see the slides, right?
So with the permission of Dr. Parihar, can I start?
Yeah, yes,
Okay.
It's my honors.
Okay. So thank you so much for this platform. So I have chosen to deliver talk over the dielectric resonator antenna, which is one of the area where we are contributing from last 10 years. So here this talk will be on the basic things, okay, on the DRA, like those students who want to start in this area, or those who want to ask actually the basic things, so they can interact with
Please switch your mic.
you can mute actually. I think we can mute all the participants. Just a minute. I think I can mute these things.
Yeah, all the participants are requested to please mute your audio, right? Audio and video both.
Yes.
Yes, sir.
Okay, so so let me introduce first my research group. Okay, so these are the full-time students working with me right now, and some of the part-time students from DRDO and ISRO and some of the Central University, they are working with me. And 5 students already graduated. One is missing here. And right now my lab's actually working towards reconfigurable metametal and metasurface compact antennas as well. And we significantly contributed to combine the MIMO and cognitive radio concepts last year. And like DRA, actually, we contributed here to have the circularly polarized wave actually within these things. And the lab is actually sponsored by the various funding agencies like DRDO, ISRO, and SERB, and my post institution as well. So these are the presentation outlines. So I will be mostly talking about the fundamentals of the DRA, correct? And we will be talking about the very small things. And finally, I'll try to connect with what we actually performed in Dhanbad actually, like development in circularly polarized DRA, and a recent contribution we made actually towards the PMC boundary approximation we will be talking about. So it's really very important actually, as the topic is dielectric resonator antenna, so the fundamental is needed here to be clear. So it is really very important. So first of all, we should understand what is DR, dielectric resonator. So this is not a new topic, first of all. It was started in 1939 actually, which Mayer introduced first time. And then after the capabilities like that, it has a very high quality factor. So if it has a very high quality factor, so we can utilize in a filter and oscillators. So earlier you can see this DR actually used mostly in filters and oscillators. And after that, these things, if you see, the papers are coming from the 2000 onwards, and this DR actually is showing a possibility that we can use as a radiator as well, correct? So how we can use this thing, because the thing is, when I'm saying that high quality factor, try to understand this thing. So this is between 6,000 to 1 lakh, correct? So with this quality factor, it is difficult to radiate actually. The electromagnetic energy bind within these things, within the DR actually very tightly. So it offers you surely the low insertion loss, correct? And here the permittivity is also between 25 to 90. So it offers you the small size. I'm talking about particularly DR actually, correct? And the good thing is that here that we don't have the conductor loss as well as the temperature, these things. We have the very good temperature stability, correct? So we can introduce the devices actually made of this DR where the environment is very actually drastically changing, like very hot or very cool. So these devices could be used if you are using this DR actually. So now we need to discuss about that how this DR become DR actually radiator. Correct. So we'll be talking about this thing, but before that, we'll be talking about a very important thing, which is a mode in DR. Correct. So the thing is here, like we all actually studied these things, your waveguides. Okay. So this fundamental mode T10, and we calculated these things, cutoff frequencies and all. Fine. Similarly here this is made of the dielectric actually. Correct. So we need to come out with some formulas or something so that it may provide you the idea about the frequency. Okay. The resonant frequency actually. So like here, this is a book actually. So you may note it down. This book is really very good book written by Casphase actually. Okay. 1986 Handbook of Dielectric Resonators on Arctic House. Okay, so this is the first book. Okay, here you can find the fundamental things as well as analyticals. Okay, the theory actually, what when the subject was started actually. So everything is given in this book. You can see this. So here we have the formula actually. So this formula could be used within these limitations when you have the aspect ratio 0.5 to 2 and the permittivity between 30 to 50. So this formula will provide you the accurate result up to 2%. So here you can see actually the field profile, particularly this E field and magnetic fields. Okay, azimuth plane and elevation plane I have shown here. So we performed over the HFSs actually. Correct. These things we performed over the HFSs and we find this text. Correct. Now let's move on how these things happen DR to DRA. Okay, so this antenna term. Now the issue is actually the question must be that the DR actually processing the very high quality factor, high permittivity, these things. So how we can use actually, how we can utilize these things as an antenna, because it may be actually very good for the designing of the filters and oscillator, because we require a very low insertion loss. But how we can utilize an antenna, and before that, why we should utilize in an antenna. Correct. So I told about the two things. One is the TCF, okay, that temperature stability, and another is that your ohmic losses. Correct. So there the two things are you can see here the advantages thing for the antenna design actually, because like the efficiency is directly actually related with the metallic losses. Okay, so this is one thing. So we don't have the ohmic losses, so surely we will be getting a very high efficiency. Correct. And if you see some of the research papers of the DRA, you will find that the efficiency is more than 90% or 95%. This is the reason actually. The second point is that it has a very stable actually stability towards the temperature. Means like if you measure your input reflection coefficient at room temperature, or if you measure input reflection coefficient, let's say at 70 degrees centigrade. Okay, so you will not facing much change actually. Correct. So this thing motivate us. Okay, this thing motivate us so we can work towards these dielectric resonator antenna. Correct. So this is the answer why we should go for the DRA actually. The second thing is that how this DRA actually become as a DRA. Correct. So let us try to understand these things. Correct. So some of the facts I have written for you here. So the thing is, this is an open resonating structure. Correct. Open resonating structure, like if you find the boundaries, so we like in most of the cases we are assuming as a PMC, perfect magnetic conductor. Correct. For the analysis purpose. Okay, earlier the thing is, but this PMC actually comes in a picture when you have very high dielectric constant. Okay, but the thing is, let's say if I reduce down, okay, the dielectric constant, okay, in between, let's say 3 to 14, so surely it will be difficult to realize me the PMC condition. correct? And hence, on the basis of that, I'm saying this is the open radiating structure. Okay. Second thing is that this is a efficient radiating modes, correct? And another point is that here we have the resonant frequency, the function of size and shape and the permittivity. So we can control these things, the band and all. And another point is that a very important point that like we can predict, okay, we can say about the far field properties by seeing the mode actually, like let's say if we are exciting with a T01 Delta mode, okay, so radiation pattern will be a broadside kind of things. For the TM01 Delta, this is a omnidirection kind of thing. So this is a very beautiful property actually with the DRM, correct? So the point is actually here what I want to make these things, that how these things become a radiator. Try to understand that, okay, we are using the low dielectric constant, okay, so that we are altering actually the PMC boundary conditions, correct? So we are providing a space to this DR to radiate, okay? So it is going to be radiated from the surface of, okay, surface of the body of the DR, correct? So like we studied about the dipole antennas, correct? So radiation mechanism and other charge neutralization and other things, correct? So here these things that these things are happening, but we supposed to provide a space for this so that electromagnetic wave should come out this thing. So if these boundary conditions are very tight, it is not possible. Okay, earlier like if you are used the dielectric constant between 25 to 100, it is really very difficult. Okay, so these are just some of the points. Okay, so we can control the size because this is the function of lambda not by under root epsilon r. It offers you the very high radiation efficiency and several feeding mechanisms you can use actually, correct? And here you can see these things that if you like earlier when we are using as a filter actually, so we are using the 2-port system, correct, and we are enclosing in the metal cavity, correct, so that minimum dissipation may occur actually from the body of the DR, okay, because this is good for the low insertion loss. Now here when you analyze these things in a HFSS, so you need to put the far field boundary condition or the free boundary conditions here. So there are some positive things, but it is not like that all the positive, some negative facts are also there. We should know about these things. First of all, the thing is the fabrication taking the high cost if you are using with the ceramics, okay, because it is really difficult to do with the ceramics. Okay, ceramic engineering is a separate branch of engineering, correct, where we are developing the ceramics and we are having a certain kind of dielectric constant. Okay, so there are certain processes, material sciences there, correct? So it is a time-taking process. That is why cost is very high. But nowadays, people are also doing with the composite material, low-loss composite materials as well. Another thing is that it is difficult to design a modified shape due to the material rigidity. These are the ceramics actually. We can miss cutting and other things. It's really very difficult, correct? If you have a very arbitrary shape, it is really challenging to do these things, correct? And difficult to get specs to dielectric materials as well sometimes. So okay, so we need to compromise with the feeding and other things so that we can get the desired result. Now let us try to understand the radiation characteristic. Okay, so that I already told these things that if you know the modes properly, correct, so you can predict your radiation pattern. So here, this pictures I have taken. This is a very well-known paper written by Mongia and Bhartiya, professor from IIT Delhi. So they actually they published this paper, Dielectric Antenna, in 1994. Okay, and this is the most cited paper in DRA. You please download it. Okay, those who want to start this things. So here what you can see actually. They given for the several modes. Okay, they given the formulas to find it out the resonance frequency, quality factors, okay, and they try to compare these things, mode and other things with the electric or magnetic dipoles as well. So like here, try to understand first, and then I'll try to prove these things. Okay, I'll give the justification as well. So first, let us know these things. Okay, so here we have the T01 Delta mode. Okay, so T01 Delta mode, what he's saying, this is a magnetic, it's X at the magnetic dipole. Okay, whereas TM01 Delta, it is acts as a electric dipole. Okay, so we all are aware from the school days, the electric dipole, what is a magnetic dipole. So this is actually these terms are making sense to us. Okay, that when I'm saying the electric dipole, so the field profile I can visualize. Okay, and this is the thing actually required when you are doing the subject like the DRA. Correct. Similarly here, like here, if you see, this is HE11 Delta mode and EH11 Delta mode. Correct. These are the higher order modes. Correct. All the components are existing here, and here they what he said actually, this is horizontally an azimuth plane actually. It is a magnetic dipole, and this is a electric dipole in an azimuth plane. Correct. So so as far as the electric and magnetic field concerned, now you can predict actually what kind of radiation pattern will be. I'll show you these things. Okay, it will be very hurry if I say all the things here. Correct. So here, this T01 Delta and TM01 Delta mode, this radiate like a magnetic and electric dipole. Correct. And now we'll see these things. Okay, that what this magnetic dipole and electric dipole is actually. Correct. So here some of the things actually he given, that for the T01 and TM01 Delta, and they given the field inside the resonator. Correct. So here you can see for the T01 Delta, the HZ component is there, and here the EZ component is there. Basis on that actually this prediction was made. Now let us classify the modes here, because the point of interest is here that how to make the DRA, correct, not a filter or oscillator. Correct. So we should know, we should aware that what modes will be helpful for us to design the antennas. Correct. So I'm dividing these two things, the high Q and low Q. Okay. So high Q, if you see the T01 Delta 01 Delta mode, okay, the offering of very high quality factors, and that is why, like, if you see in the literature, you will find that mainly this mode actually exploited in designing the filter and oscillators. Whereas for the low Q, okay, this is low Q is TM01 Delta and HE11 mode. Correct. These are the two modes, and the TM01 Delta mode offering you the omnidirectional radiation pattern, and the HE11 Delta mode offering you the broadside radiation. I'll show you these things. Correct. So now this thing is clear that we have to stick over the TM01 or HE11. Even I'm not you can also use the T01 Delta mode, because maybe some for-field requirement and you can fulfill with this T10 mode, but maybe the efficiency and other things you have to compromise it, these things. Correct. Many paper you will see the T01 Delta mode also used actually as a radiator. Okay. So now the thing is, let us try to understand T01 Delta mode. Correct. Fine. So here, this is the picture you can see at the left hand side. I have taken from the Casfield's book. Okay. Or you can see this paper actually he published in 1984. Okay, and he given by the computational technique and all, he tried to give that time 1984. That was not that time means HFSS and CST, these things were not there actually. So people are doing this computational and other things, and they are deriving equations and predicting the facts actually. Now the things are very easy. Okay, so here you can see these things. We try to verify. We try to verify it with the HFSS. Okay, because as a PhD student, like most of the students are, I think, here. So like MTPG students, so they can you please mute? I think someone is unmuted, so kindly mute. So here like we need to verify it. Okay, so what I did these things in eigen mode analysis, correct, in HFSS, and what I find that the first mode, which is the T01 Delta mode, and exactly the same field pattern I got. Okay, so why I'm doing these things? Because if I'm starting the subject, okay, for the PhD student particularly, if you are starting the subject, you should be assured, okay, that whatever you are doing, okay, you are going in a right direction or not, or the earlier knowledge produced is correct or not. Fine. So this is the responsibility we should check also. So here now we'll try to understand this magnetic dipole, these things. So here, this is, as I told you, this is going to use as a filtering and oscillation, these things. So here you can see this is the magnetic field, correct? And if you recall actually magnetic dipole, okay, so the magnetic field is like that, correct? On that basis actually, this is called as a magnetic dipole, correct? I hope this is clear to you. Similarly, if you do for the TM01 Delta mode, okay, and if you see the electric field in an elevation plane, correct, and this will provide you the sense that this is actually what? This is the electric dipole, okay, this is the electric dipole, okay, and you can see we compare the things and we find that everything is fine actually, whatever he given is fine. Similarly, we did for HE11 Delta mode also, correct, and all the simulation work I did on the eigen mode analysis. Okay, please take care. This is not a driven model. This is on eigen mode analysis. Fine. So it will provide you the broadside radiation pattern as well. Correct. Now, like here, if you see, okay, I just missed one point. Like I'm saying the omnidirectional radiation pattern. On what basis actually I'm saying? We should try to understand. Like if you recall the dipole antenna, correct? If you recall the dipole antenna, you can predict the current profile over this thing. So this is a half sinusoidal. Remember this thing, half sinusoidal, correct? If you find it out the electric field, okay, so the electric field will be like in this fashion, and the magnetic field around the dipole is like that. So this is almost same actually what we learned in a dipole antenna, lambda by 2 antenna, correct? On same thing we can observe with this DR when we are exciting the TM01 Delta mode. Okay, now the next question should be that how I'll excite the TM01 Delta mode. I'll give you the hint. Okay, I'll give you the solution actually in a coming slide. But how we can excite this TM01 Delta mode. Okay. Similarly here the HE11 Delta mode. Okay, we verified in all the planes. Now this is somewhat these things very interesting. I think some participants are waiting. No. So they basically, if you see the three conventional shapes are there. One is the hemispherical, cylindrical, and rectangular. These things. And basis on that, actually, we divided the radiating and non-radiating mode, means high Q and low Q. Okay, so like for hemispherical DR, okay, what we find the T101 Delta is a non-radiating mode, whereas for the cylindrical DR, T01 Delta, we are saying the non-radiating because maybe these things, radiation efficiency and other things are less as compared to HE11 and TM01 Delta mode. Okay. And the rectangular DRA, here this is our relatings are T2Y11, T2Y113, and T2Y311. Correct? These are the relating modes. Correct? So you need to take care actually, because you need to understand the coupling mechanism and other things. So when you couple these DR actually, so this mode should be come out, okay, within the DR. Okay. Now the next thing is that prediction of the resonant frequency. Now, what Casphase actually, 1984, what he did, he given a formula to calculate the resonance frequency for the T01 Delta mode. And The logic behind this is that this is completely on the analytical solution, based on the analytical solution, these things, that formula, and he able to find it out, the resonant frequency formula for T01 Delta Mode, correct, after this several these things, derivation and other things, okay, and it was actually in a closed boundary, correct, in a metallic shield, he assumed the boundary condition as like that. But what about the antenna, correct? Here the boundary condition is open, okay, or ABC, fine. So the thing is, the boundary conditions change here, correct? So that we need to think, okay, how we can find it out. So still, many research groups are struggling to find it out, the resonance frequency, correct? There are other way also, but still the closed formula is difficult, very difficult to do. So what Monge actually did, he used actually he used the data of the several experiments or the simulation, and by the curve fitting these things method, he come up with some formulas, correct? So they call it as an empirical relation actually, correct? So he given, like I have just taken the T01 Delta Mode here, correct? So this is the formula, okay? So this formula is valid with certain limitation, like aspect ratio must be 2, correct? And for permittivity between some numbers, like I think this is for 6 to 10, correct? So some boundary actually is there, and within that actually you can find it out. And if you go beyond this, you have to rethink, right? So this is one way actually to find it out, the resonance frequency reported by the Monge, correct? But what I suggest you that when you are going for the arbitrary shape or the different, this is for cylindrical DRA, correct? Yeah. So you need to think. You need to analytically. I not suggest because it will take a lot of time. So what you can do, you can use HFSS, correct? You can use the driven mode analysis, and if you excite successfully particular mode, so you can predict the resonance frequency as well, correct? I'll show you these things. Now, let us try to understand the coupling mechanism, okay? So as I told you, there are several coupling mechanisms we can use, okay? So here we have to excite the EM power to the DR, fine, because we are talking about the electric dipole, magnetic dipole, and other things, fine. So how we can excite, okay? How we can couple actually that mode. So like if you recall your UG days, okay, you perform the experiments in a on a microwave bench, correct? And that bench was actually T1010 mode actually, okay, which is a fundamental mode, and we are running all the operation, all the experiment over that mode only, correct? Have you tried to open, okay, the waveguide and try to understand how this mode was excited? So like I'll tell you these things. Like if you open up this thing, so there will be pin actually, correct? A very small pin there, okay, just before the waveguide started, and these things, the current is there, and due to the current you have the magnetic field and the position at the middle actually, so that you will be getting the maximum this thing, fine. So similarly here actually, when we are talking about the DR mode, okay, like for the TM01 Delta Mode or T01 Delta Mode or T1 Delta Mode, so we need to first recall that what is the electric field and what are the magnetic fields, okay? Means like, let's say if I'm saying that TM01 Delta Mode, so as I have shown you the field profile, okay, then azimuth plane we have these things, the magnetic field, and elevation we have the electric field, okay? So what we'll do, we'll put a probe, okay, in a center, at the center of the cylindrical DR. So there will be magnetic field around this, and on the elevation plane we have the electric field. So hence we can say we perfectly realized actually the electric dipole, correct? So this is actually this is very important that we should aware about what kind of electric field and magnetic field for the particular mode, correct? So this will come with the practice, and when you run the simulation, will try to understand the field profile. Okay, you will be getting sense that yes, I should put the probe here, I should put the slot here, so I'll getting the field of this kind. Correct. So here there are 5 coupling techniques. I'm showing here the coaxial, microstrip, conformal, aperture, and coplanar. Okay, so means like if you use a coaxial for certain advantage and disadvantage. If you are aperture, definitely some advantages will be there, and definitely some disadvantages will be there. So means basis on your requirement. Okay, you can utilize any of the coupling mechanism. Correct. So I'll show you this thing so that you will be getting idea that how I will couple actually this DR, okay, with this excitation mechanism. Correct. So now let us start with the coaxial probe. Correct. So this is the coaxial probe. Correct. If I ask you to draw the electric and magnetic field, this will be like this. Correct. Electric field will be coming out like this, and this is magnetic field around the probe. Correct. So now just take some examples here. Correct. So there are 3 geometries I have shown here, 2 geometries and 3 locations. Okay, so this is a cylindrical DR. Okay, and at the center we are feeding. Here you can see we are feeding through a periphery. Okay, and again if you see this is a rectangular DR, we are again feeding through the periphery. Fine. Now the thing is, if you like from the very basic, actually you can predict that what kind of field profile will be there. So for these things, like in a center there will be magnetic field around the probe. Okay, like this, and there will be electric field. Okay, so this is what kind of mode? This is a TM01 delta. Okay, this is a TM01 delta mode. Fine. So for the TM01 delta mode, the radiation pattern will be similar as lambda by 2 antenna, which is a omnidirection pattern. Okay, remember? Fine. So now you can predict actually, okay, the radiation pattern here. So the radiation pattern will be like this. Okay. Now if you see this cylindrical DR, okay, fed through a periphery. Okay, at the circumferences, these things. So there will be electric field will be making a half cycle, and there will be magnetic field like this. So this is, if you compare the field profile, you will be getting that this is a HE11 delta mode. Correct. And because the electric field is like that, so it will be going upside these things. Okay, and here you have this thing, radiation pattern in a directional in a theta 0 direction. Okay, so similarly for the rectangular DRA as well, correct, this will be TE01 delta mode, and you will be having this kind of radiation pattern. So quickly, okay, very quickly you can predict what kind of radiation pattern you will be getting these things. Now coming over the microstrip, this thing, so here you have this feed line. Okay, and this is the field profile. Okay, this is the field profile. So like there may be the two possibilities here. One, we can put the DR over the feed line, or we can put side by side. Correct. So what will happen? You can see here, like if you're putting over the this thing, so feed line. Okay, so this will be the magnetic fields. Correct. This will be the orientation of the magnetic field, and here when it will interact with the DRA, the field lines will be like this. Correct. Okay, it will be stretched like this. Okay, now if you if you try to couple side by side, okay, so the field will be like this. Correct. So here the orientation, let's say in X direction, here this is the Y direction. So now you can predict some of the properties. Okay, particularly far field properties, how it will look like. Okay, so we done some simulations here. Correct. Like here, if you see the cylindrical DR. Okay, let us be focused on the cylindrical DR. Correct. So cylindrical DR, we put it over this thing, and what we got, this T01 delta. Correct. This is, we got the T01 delta mode. Okay, so sorry, this is actually the cylindrical DR. This is for HE11 delta mode. So here we have the field profile like this, and we have these things, radiation pattern, like the directional radiation pattern, correct? Similarly, the conformal strip technique, okay? So we have the monopole kind of situation once again, and the same thing will be happening like what we have seen a probe coupling. So here you can see we can easily excite the HE11 delta mode, okay, by just putting the conformal strip over the surface of the cylindrical DR. Now, this is somewhat very interesting, and you should know these things, that aperture technique, correct? So, like the slot, when we are exciting with the slot, correct? There are advantages, there are disadvantages as well. Like many of you perform the simulation, and you find you have experienced that when we are exciting with the slot and other things, so we will be getting the very low bandwidth, correct? The reason is that the fields are very tightly bounded here within the slot actually, and this is the direction of the fields, correct? When it try to come out from these things, so if you put the DR over these things, okay, so it will be precisely exciting a particular mode, okay, because here you are not going to give the room to this electric field so that it will create some fringing field and other things, correct? And that is why if you see the cross polar component here is very, very small, okay? So let's say if you get some challenge that you have to design an antenna where the cross polar component should be very low, very, very low, so definitely I'll recommend you to use the slot excitation, correct? So the similar kind of mode you can get if you excite like this, so you will be getting the HE11 delta mode once again, okay? Similarly, the coplanar waveguide technique is very important nowadays, because we want to put all the things on the same plane, okay? Coplanar, these things, ground, circuit, everything on the same plane, correct? So if this is the situation, you can definitely go for the coplanar waveguide. So what we have seen, we experimented here and on over the HFSS, and what we find that we successfully excited the HE or TE mode easily in a DR and rectangular DR. Fine. So basis on that, actually, we made some comparison. Okay. So as I told you, I'm not saying this technique is good, this technique is bad. Depending upon the situation, you can adopt these things and you can work. Correct. Now, this is all about the basic sense. Okay. This is all about the basic sense of the DR. Fine. Now, some analysis part I would like to discuss with you. Correct. So earlier, like why I'm showing here this thing, try to understand, because nowadays if you see in a paper, so different structures are coming with a DRA, but the students are trying to calculate the resonance frequency and other things, okay, with the same formula given by the Mungia and this thing. This is not going to be work. Maybe, okay, you are getting results somehow, correct, changing some of the things in a formula, but this is not correct thing, okay, because the thing is, those formulas are the empirical formulas, and this is done with some experiment, number of experiments were these things was performed actually, and then this formula was came. Now if you have any irregular shape or a new kind of shape, okay, so you can start this thing. I'll give you some hint, okay, so you can, so definitely we should start with the Maxwell equation, and you have to write this thing, Helmholtz equation and all. And because let's say if you are doing for the cylindrical system, okay, so like here this is for the cylindrical DR actually, so you have to write all the things in a the cylindrical coordinate system, okay, so you have to find it out all possible components there, correct? So this is very well known thing, magnetic wall method, correct? So earlier it was done with the PEC was there, this in a cavity they suspended a DR like this, and they try to find it out the electric field is EM energy stored actually in a various section. Okay, and finally they use the cavity perturbation method to find it out these things. Fine. So they did for that HE11 delta mode here, correct, and they try to find it out the different field components for that, and basis on that actually they find it out the field components at different regions. They divided region 1 and region 2 and this DR actually. Okay, and they try to find it out all the field in a different region. Then after, if you see here, okay, then they apply the boundary conditions here, means the similar process actually what we have seen, and they come up with some solution, transcendental equation kind of things, and finally they solve for the beta. Once you have the beta, you can then find it out your cutoff frequency or this resonant frequency, these things. Fine. And later on, the people will also perform with the perturbation correction also. So what they did actually, they instead of making the 2 regions, they made here the number of regions are 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, 9 regions are there, and they try to find it out these things. And basis on that, they use the cavity perturbation formula. I believe you must have seen this formula, and they try to calculate the energies in different regions, and they try to fix these things. Okay. And this is the formula already I have shown you. This is done by the Monge actually, but it has certain limitations. Okay, so the thing is, the students here, okay, what they can do actually, there are number of irregular geometries are there. They can take as a challenge and they can derive some of the things and they can find the solution. It will definitely a contribution in a basic theory. Correct. Now. So this is a simple DRA we performed on this thing driven mode analysis here, and here you can see these things. Here the height and this d by h is 2 we have taken, and this is a proof fit, correct. And basis on that we try to analyze the different parameter like the dielectric constant, length of the ground plane, so many things actually. Okay, and we run the parametric studies and all, correct, and we find it out some of the things. So this we are trying to compare the result of the formula, okay, by the Monge and the HFSS. So what we found different in the certain these things boundaries actually what the Monge made, the formula is correct. And then we used the multi-layer multi-permittivity approach actually, and we excited through the surface, okay, and we again got a similar kind of result. So here you can see this is a 3-layer system here, and we try to find it out the HE11 delta mode, and in all case, okay, we successfully excited the HE11 delta mode. Fine. So the conclusion is that like first we need to ensure, okay, what is the mode actually. So you need to perform the driven and these things eigenmode analysis. Okay, and we verified these things once again. Now, so this is all about the DR actually. Now, what we contributed in the circularly polarized DRA, correct? And also in a wideband DRA also we worked, but recently we contributed in CPDRA. Okay, it's a very good area to work actually, because the CP antennas are required, because like MIMO antenna, and then we have if you include the CP property as well, this is a good addition. So let us try to understand the circularly polarized antenna. So we can divide as a narrowband antenna and the broadband antenna. So you must be knowing about the uniform helical system, these things, correct? So this is going to provide you a CP waves here, and here if you tapered it, okay, if you tapered it, you will be getting the wideband as well. Okay, so this is the conventional one. Fine, and the basic idea, I believe you know, this is electrical polarization, and this is the equation here we have. Fine, and the axial ratio we are defining as max E max over E min. Okay, so particularly like if you see the circular polarization, correct? So here the idea is that the magnitude should be same, okay, and the phase difference should be 90 degree. Fine. Okay, so this is space and this is a phase. This should be orthogonal. It's EX and EY should be orthogonal, and phase difference should be pi by 2 also. Correct. So taking care of these things, so we have number of benefits here. Correct. So here you can see these two pictures are very clear. Now, if first you need to arrange two orthogonal components, let's say E1 and E2, and then you have to make a delay in time. Correct. Or these things in degrees, this is 90 degree. Correct. So what are the benefits? It will offer you the higher link reliability, and these things it offers you these things possibility of means the signal is not going to be loose actually in a different atmosphere condition and all, because it is not going to be these things depends over the orientation of your receiving antenna, these things. Correct. So but there are some disadvantages also, like if you have one linear polarized antenna, other is circular polarized antenna, then the power will be divided and you have the gain the deficiency in the gain actually. Correct. So this is the thing. I'll not take much time here. Correct. Because I think I have 10 minutes. So quickly I'll show you this some of the work actually we performed at Dhanbad. So this is some of the thing. These are some figure by which we can understand the LSCP and RSCP as well. So this is, I think, the good picture. Like if you have the wire antenna, loop wire, okay. So if you feed from here, okay, the current direction will be like this. So it will offer you the LSCP. If you feed from this side, the current direction will be like LSCP. Correct. So this is making sense, I believe. Okay. So just going to these things. Okay, so let us talk over the CPDRA actually. So here it depends on the feeding structure. If you see in a literature, you will find that there are mainly three feeding structures are there. One is a single feed network, dual and multiple feed network, and sequential feed network. Correct. So you need a single feed system, means like you have to find the degenerate modes and all. Or here, if you have the dual feed system, so you can produce the orthogonal fields at least, and by varying the locations, okay, you can also manage this phase delay also. Correct. Sequential is well known that these things that different components will be there and offering you the orthogonal. Provide you the possibility of getting the orthogonal components. Fine. So here there's an example actually for you. Let's say if you have a linearly polarized DRA, correct, and if you're able to excite EY, okay, EY component, and this is coming with the T01 Delta, and if you have another DR, linearly polarized DRA with EX component, okay, now you have to manage the time delay, and if you able to find the coupling here so that you can merge, so it will provide you the circularly polarized wave within the DR. Correct. So this is actually basis on this fact actually. So this is a very simple structure. Correct. We have just taken the cylindrical DRA and we fed from the two locations. Correct. The two location means that we are arranging the two field components, two orthogonal field components, and here if you see we are exciting from the surface or wall of the DR. It means that what kind of mode? This is the HE11 delta mode. So when we have HE11X and HE11Y, correct? Now the two modes, okay, orthogonal modes we have. So surely we will be getting the orthogonal component. Now the next thing is that we supposed to arrange, okay? We supposed to arrange the time delay, correct? So I'll show you that how we perform this thing. So here we have the arrangement like this, correct? Here you can see this is a right angle strip you have, and over that we have the conformal strip. Okay, fine. Now what we did actually, we started with the HE11 delta mode. You can see the figure number A. Then we introduced here a right angle here, correct, so that we can put another strip here. Fine. So like for this case we have HE2X11 delta, and for this things still HE2X this thing, but here you can see some matching issues are there. Now once you remove the probe or the conformal strip from this point and we are putting this side, so you will be having the situation like this, and you will having a mode HE to Y11 delta, but this time you have some shift in frequency. And why this shift in frequency? Logically, this should not be. Okay, why? Because you can excite from any side this thing, the resonant frequency should be same. But here, due to this extra arrangement, actually, you can see here, due to this extra electrical length, okay, their shift is there. Now, when you are combining these two strips, so you can clearly see there's a two modes actually, correct? One may be this things, and another is right angle plus this strip, correct? So here, what we have observed this thing, depending upon the vertical strip, okay? So when we got V1 greater than V2, what is V1? V1 is this and V2 is this, fine? So when we have the V1 is greater than V2, so we have the RSCP, okay? Right hand circularly polarized wave inside the DR. Whereas when we have the V2 is greater than V1, we have this kind of LSCP. And when we have V1 is equal to V2, correct, we are able to maintain the orthogonal field component, but we are failed to introduce the 90-degree distance phase or the delay actually, correct, and hence we have the linearly polarized this thing. And this could be confirmed by the axial ratio plot as well, correct. So instead of that, we also tried some different arrangement also, like instead of the this right angle strip, we can also go on the periphery of the DR also. But the thing is, in this way we are increasing the length, also we are introducing the ohmic losses, so we should not, we are avoiding these things. Okay, this is just for the knowledge that yes, this is a possibility and what will happen if we do these things, correct. So finally we measured all the things, and what we found, the things are very promising with the simulation one, correct, and it is actually working at sub-6 gigahertz band, correct, and providing a sufficient axial ratio bandwidth, 24% around, and the gain also is really these things you can see here. Now this is the recent contribution actually from my lab. So here we made some a new kind of idea actually given, okay, because like I have shown you three kind of coupling mechanism, correct, that is fine, but can we do with changing the shape in a DRM? But if we are changing arbitrarily, then what will be the explanation, correct? Maybe we will be getting some point of alteration, but we need to come with some logical or reasoning actually why the things are happening. Okay, so here we provided a solution of rather to say actually this is analysis, okay, a close analysis by using the perfect magnetic boundary conditions, correct. So here the idea is that this is the proposed antenna configuration here. So here you can see we have a DR actually, and you can see here we have taken the number of layers actually, and we put it in this fashion, a stair kind of thing. Fine, this is a stair kind of thing. If you see, this is a 4 layer, correct. So we remove the 1 by 4 here, then after gradually we are removing this thing, then half this thing. So why we are doing this thing, correct, and what is the benefit? Now here if you see this phase 1, okay, this is the phase 1. I'm saying this one, please mark the cursor, this is the phase 1, and this phase 1 and phase 2, if you compare, this is a 45-degree angular displacement, and then between 2 and 3 again 45, and 3 and 4 again 45, which means that 1 and 3 90-degree, and 2 and 4 again we have a 90-degree. Okay, now why we are doing these things, correct? As I told you, to have the CP actually, okay, there are two conditions. One is the orthogonal field component in a space, and we have a time delay actually, or this phase difference between this 2x 90-degree, correct. So first of all, because this is a single feeding system, this is simply we fit through probe, okay, we fed through probe actually. So we need to arrange the orthogonal component. Fine. So if you see here, we have taken the PMC, perfect magnetic conductor boundary condition. And what is happening actually with the PMC actually, that you must be aware about the PEC, okay, perfect electric conductor. So what is the tangential component of electric field is 0, remember, and the normal component is the magnetic field. Now dual of this is the perfect magnetic conductor. The tangential part of H, okay, will be 0 here. Fine. So here now this is making sense here, okay, that between these two there will be orthogonal component, and it means the on the face of 1 and 3 and 2 and 4 we have the orthogonal component. Okay, and this could be verified from here also, like from this is the first, these are the 4 iteration here. You can see the phase 1 we have the tangential E field here, correct? Okay, there must be some tangential E field. Magnetic field will be 0, but tangential field will be there. Now what we did, we just taken out some of the part, and this is the 45 degree this things. Then again we removed some of the part, it's making the 45 degree, okay, and now phase 1 and phase 3 having the 90 degree apart. Now here what we have observed that the tangential electric field is also interact over this change also. So hence on basis of that actually we can say this thing, that these tangential E fields are orthogonal on phase 1 and phase 3, phase 2 and phase 4. Okay, so this is the basis of, okay, having the 90 degree this things. Okay, so now we manage these things, orthogonal field component, okay, and the location of this probe, okay, this location of this probe will provide you the 90 degree between this electric fields, generated electric field on the phase 1 and phase 3 and phase 2 and phase 4. Because this is not at center actually, so we run some simulation and we find this location, that yes, we are getting some phase change between the components, correct? So this is a very complex one, okay, but here you can see the simple idea is there, correct? Yeah, sure, the phase and other thing is very tricky, and while measuring and other things we need to take care of these things, correct? So after that we have we went through some other iterations also, like 30 degree, 60 degree, 90 degree and all. We checked actually that we are curious to find it out that yes, can we get some better results from other segment also, correct? So it was what we find that 45 degree is a suitable one, and we are getting the good axial ratio bandwidth and all. Fine. So the concept is this actually, and finally we have given some design rule, so you can refer this paper, these things. I think we don't have time also, so we publish these things in IEEE WPL. You can find these things. So clear-cut design guidelines and everything is given, so you can have a look. This is really very good work done by one of my students, Rakesh. And finally we measured and we find that the results are very promising actually. Some changes and some things, some problems are there, okay, because in simulation we did not actually consider the layer system, but in reality we are having the layer system, and these things 10 delta and permittivity issue may be there because this is a very conventional material, AL2O3, correct? So we also checked with this rectangular, this concept actually, this concept staircase system. We checked the rectangular side also, and we got the acceleration. So this is well proven concept. Even you can go with some other geometries also. You are free to use these things, okay, and you can get maybe the better result on this. Okay, so this is all about, and these are the references actually, correct? And I would like to acknowledge my PhD student, Dr. Rajkishore, and Dr. Rakesh. He is also completed PhD last month. Okay, so they contributed significantly. So this is all about from my side, and thank you. And if you have any questions.
Thank you so much, sir, for this vibrant lecture. You have covered so many topics like modes in DRA, radiation characteristics, and coupling mechanism, feeding techniques, calculation of resonance frequency and polarization. So we can have, with permission of you, a couple of questions.
Yes.
Sir, can I ask one question? Sir, what is the difference between regular DRA and hybrid DRA, sir?
Pardon?
We have this rectangular DRA and cylindrical DRA. Now there is a hybrid DRA. There's some of the papers
Hybrid DRA is not a new term actually. Means all this DRA, these things are hybrid actually. Okay, all this DRA is a hybrid actually, because when we are seeing the rectangular or the cylindrical DRA, so we are talking about in terms of the suspended structure. But here actually we are feeding through a microstrip. Okay, so some of the characteristics are coming through the microstrip feeding, and some of the characteristics also coming from the DR. So this is a combined business actually of the DR and the microstrip. Correct. That is why we are calling it the hybrid DR. Correct.
Means the feeding structure, if we change, means it is a complex one, then will it be called as a hybrid DRA, sir?
Simply you can say DRA plus feed is a hybrid DR.
Means a simple microstrip, or it should be some complex, sir?
Maybe simple microstrip also. Correct.
Microstrip can also be called as a hybrid DRA, sir. Hello.
One question. How DRA radiation mechanism differ from conventional antenna?
Hello.
How DRA radiation mechanism differ from conventional antenna?
Yeah, as I told these things, like what kind of conventional antennas? There are number of conventional antennas. Correct. So like if I just take it out the lambda by 2 antenna, so there is a charge neutralization techniques. Okay, we are making the charge neutralization over the body, and then only the EM wave is going to detach from this thing, and hence we have the radiation. Here in a DRA actually we have the low dielectric constant, correct, and we are avoiding actually the PMC condition, and hence this electromagnetic waves are leaking through the body structure of the DR, and hence we have the radiation from the DR.
Sir, one more question, sir. Sir, regarding this DRA fabrication, no, sir, we will be keeping this DR on a substrate, no, sir?
Yes.
So if we take the boundary conditions, only the bottom wall, if we take this along x equal to 0, that will be a PEC, and all the walls will be a PMC, sir. Yeah, am I correct, sir?
Like a boundary far field, you are talking about the far field distance. For far field, calculating the far field, correct?
Yeah, sir.
Okay, so for that actually, you require there is a provision actually in HFSS. Okay, there is an open boundary condition, and particularly if you go with the FTTD, correct? If you want to write your own code, you have to write the code for ABC. Absorbing boundary condition. Okay, so the nothing should go out and nothing should reflect back. So for that actually we can calculate the far field this time. But the thing is, if you want to calculate, okay, it's resonance frequency. So that time you have to use the boundary condition what you said actually. Okay.
Okay, for resonant frequency, only the bottom x equal to 0, it will be a PEC, and all the balls are PMC, sir.
It depends actually in what environment we are using, because again, like all the analysis and other things happened actually with the suspended DR. Okay. So if we are changing the boundary conditions, surely the things will be changing. Okay. So you have to keep this thing in your mind. Okay.
Practically, sir, we will be fabricating on a substrate, sir. We're keeping losing.
So I'll not recommend you to find it out the resonance frequency with this actually, because this is now a very trivial process. You can go to the driven mode analysis or the eigenmode analysis, and you can have a sense that yes, this will be the mode actually, and at this frequency, okay, or at this point I'm getting this mode. So easily you can this thing. The only thing is that when we are calculating the far field parameter, so by the
the second half.
Which DRA?
Yes, not DRA, sir, especially this modes and all this. boundary conditions, this modes.
Modes and other things, actually, I already told that Professor Mondia, he developed.
That is paper, no, sir.
So you can find it out.
Sir, we can have one more question. What is the difference? What is the difference
Hello?
between? Yes, sir. We have one more question.
Haji.
What is the difference between radiating and non-irritating modes, and which modes we should prefer while designing the antenna?
So as I already mentioned this time, that radiating and non-radiating mode, correct? Why I'm saying the radiating and or confined or non-confined, you can also say. It depends on the quality factor, actually, correct? So like if the quality factor is very high, so what do you mean by if the quality factor is very high? It means the energy, okay, is going to bind very tightly inside the distance, your DR actually, and it is very hard. It will be difficult actually to radiate, and maybe if you are managing the boundary conditions such as, so it may radiate. So you may be compromising with the radiation frequency, correct? So on the basis of that, actually, I'm saying that this is a non-radiating mode, but this will be not the correct term. You can say the confined mode. Okay, so confined mode may be the difficult to radiate. Fine. On the other hand, if you try to find it out the quality factor for the higher order mode, you will see that with having the permittivity between 3 to 14, the Q factor is very less. Okay, and that time these fields actually loosely bind actually within the DR structure, and these fields may be released easily actually. So basis on that, I made the two categories actually. Okay, low Q and high Q, or you can say confined, non-confined, like that. So for the cylindrical DR, you can use T01 Delta Mode or TM01 Delta Mode. You will be getting the very good efficiency. Okay, as well as bandwidth analysis. Fine.
One more question, sir. How the higher order mode enhance the gain of DRS?
Pardon?
How the higher mode, order mode enhance the gain of DRS?
The thing is, like when we are using the higher order modes, okay. So maybe I'm not saying that always actually, correct? Maybe, okay, you will be getting good gain in some of the regions actually, okay, because due to the complex nature of the electric and magnetic field in a higher order modes, okay, so you may be having that time very low Q radiation there, okay, and hence you have the high quality factor. But I'll not recommend these things that you use a very higher order mode for getting these things. You may have the other arrangement also for getting the higher gains actually, like using the artificial magnetic conductors, okay, or maybe have the FSS you can use, okay. So the best thing would be like that if you're using this starting 4 or 5 modes, so you can predict radiation pattern very easily. If you're using the very high order mode, what will happen? The radiation pattern and other things is very irregular and may not be utilized, may not be used actually for medical applications, correct? So we need to see these things, correct?
Sir, one last question, sir. Can I ask?
Okay.
Sir, regarding this is in research paper, sir. So in antennas, we will draw this diagrams now, sir. This whatever the DI diagrams. So what is the software which we use to draw it, sir? So we should not take the picture from HFS or CST directly and we'll put in the research.
You can use Visio software. You can design this Visio. I mean Microsoft Visio is there. Okay, you can use.
It is a free software, sir.
Yes, I think 2013 we are using. We have the license.
Okay.
One more question. Sir, please tell me something about fabrication tools and method and some companies for fabrication.
There are number of companies are there. Correct. Write to me. I'll reply.
Okay. So now there is no question more, and I hope that all participants will get the motivation by this work and your lecture. So I would like to now invite Dr. Manoj Singh Parhar sir to say a lot of things.
Yeah. Thank you, Dr. Raghvendra, for a very interesting and informative talk.
Thank you, Dr. Manoj.
I'm sure that all the participants enjoy this talk and gain a lot of knowledge about DRA, which is very, very gray area or promising area at present scenario to design RF radiating and resonance system, right?
Yes.
Thank you very much for accepting our invitation, our student branch and MTT-S chapter invitation to deliver this wonderful talk.
Okay.
And I congratulate the IIITDM student branch and MTT-S student branch chapter and their officers for organizing such a wonderful event. And I thank all the participants also who attended this talk and enjoyed this talk and got knowledge. Thank you very much. Thank you very much, Dr. Raghvendra.
Thank you
for spending your time, valuable time. Thank you very much.
Yeah, thank you.
Before ending this talk,
The students will be keep in touch with you for further, maybe for a few further talks.